So I like this video game controller thing I have here on my head, so I hope everyone can hear me. So, I was talking with Duparnab, and there's a lot of important scientific questions about community detection and what is it, how do we validate it, and what do we think it's good for anyway, and what do we do when the model is wrong? And after all, like I said yesterday, real networks are not generated by the block model that I discussed yesterday, or by really any other model. So what do you do when the model is wrong? Even if you believe the model, what do you do when you don't know the parameters? How do you find the parameters? How do you determine the number of groups, and so on? And if you have multiple algorithms that give you different community structures, how do you tell which one is better? And so I just want to address some of this briefly, and maybe we can say something at the end as well, before we get into the math questions, which are different from the science questions, although they're also very nice. So from my point of view, when you're doing statistical inference and you're trying to, for instance, find communities in networks, you should always have an application in mind. And so we saw yesterday that if your measure of the goodness of a community structure is how good it looks, and indeed many people use community structure primarily as a method of visualization, which is important because we need to be able to visualize data sets, that can be misleading. So, because it can often be that lots and lots of different structures look good, which have nothing to do with each other. So, in a lot of the work on community structure, what people do is they run an algorithm on a network, and then they compare what the algorithm said with some ground truth, which is really some human who's looked more closely at the data, who, for instance, has classified the blogs as Democratic blogs or Republican blogs or something like that. And then what people say is, well, if my community structure algorithm produced communities that are strongly correlated with this ground truth labeling, that was good, then we win. Okay, well, the only problem with this is that by definition, then you're only going to learn things that you already know. So I guess if your algorithm does well in a lot of networks, then you might hope that it will also tell you something about another network which is too new or too large or something to have a human already figure out this ground truth. But on the other hand, this isn't always a good approach. So one of the networks that we looked at was a network of about 500 species in the Antarctic Ocean, and it's a wonderful data set. We got it from some ecologist trends, and it's a quite rich data set. So there are links in the network, as in species A eats species B, but then each species also has multiple different pieces of metadata. There is whether it's an herbivore or a carnivore or a detritivore, which means it eats the stuff which is floating down in the sea. And then there's another column in the database about, is it benthic or pelagic? You get to learn lots of new words, right? So benthic means it lives near the sea floor. Pelagic means it lives near the surface. Demersal means it lives near the shore. Okay. So you have multiple pieces of metadata, and then a given algorithm might agree with one of these pieces of metadata, but not another one, and so on and so forth. So, and then you start to feel that if you're saying that the algorithm did well or badly, depending on whether the communities agreed with this piece of metadata or that piece of metadata, you start to worry whether that really makes sense, in my opinion. So there's also this phenomenon where, for instance, I showed you yesterday this blog network where there are these, in this community, there is a very central high degree node, or several of those, and then a bunch of low-degree peripheral nodes. And then in the other community, you have the same thing. And then there's lots of edges within communities and a few edges between communities. So a lot of networks look like this. So I didn't say this yesterday because it's slightly embarrassing, but the standard block model that I described yesterday, if you just say, well, there are two groups of nodes, but I don't know anything else, find me the two groups of nodes. It actually prefers to divide the network this way. It says, oh, I see, there are two kinds of nodes, the high degree ones, the central ones, and the low degree ones. Did I get it right? And well, it's not wrong. There is that kind of structure in the network. It's just not the structure we had in mind, which was to divide it into these two groups. So briefly, the reason this happens is that the block model I described, within each group, the degree distribution, the probability distribution of how many neighbors you have is Poisson. So, which is fairly peaked and which very rarely produces high degrees. So the standard block model, the vanilla block model, looks at this network and it can't believe that these could be in the same group as those. So the only way it can deal with these very different degrees is to put these in separate groups. Well, okay, but that's because this graph is not well modeled by the simple block model I described. So if you have two groups, the Democrats and the Republicans, the model that I described simply will not produce Democrats with a degree of 1,000 and also Democrats with a degree of 3. So, fine. So we should change the model. So there's a variant of the block model called the degree-corrected block model, where in addition to which group you belong to, every node also has an expected degree related to its overall popularity or something like that. And then that affects the probability of a link. And then that model does fine. It immediately divides this into the left and right factions that we wanted, because that model doesn't mind, it isn't surprised by the idea of nodes within a group having very different degrees. So I guess what I'm trying to say here is that there are lovely math questions about each one of these models, but of course, as scientists looking at real data, we have to be willing to reject our models and change them and so on. And you know, that's also, thank you very much, that's also where the orthodoxy of Bayesian inference kind of falls apart. Because, you know, you could pretend that, oh, well, both of these models are in a sort of bigger model space and I had some prior on this and that, and then I'm rejecting this one in a Bayesian way and updating my posterior on that one. But that's not really how science works at all. Instead, you fit a model perhaps in a Bayesian way in that model space, and then you do some tests, some scientific tests to see if it does a good job, and if it doesn't, you throw it out and use a different model entirely. The other thing I want to say is that, so let's go back to this question of when is a community structure algorithm good? So, of course, you can test it on synthetic networks made with this model, but that's kind of cheating because, of course, a synthetic network made with a given model will be fit very well if you use that model and if you know the parameters with which you generated it. So with real networks, we talked about matching metadata, but the fact that that can be problematic. So there are a couple of papers saying that if you look at the topological communities, the communities defined just by the graph, these often don't agree with what people call the annotated communities, or if you like, the metadata communities. So there are a couple papers out of the group at Stanford saying, if you look at Facebook, for instance, then the topological communities, the ones that community structure algorithms find, are often not that strongly correlated with your taste in movies or things like that, the metadata having to do with these people. So one point of view is that, well, then these communities are just wrong. All right, well, that's true if the reason you were looking for communities was, for instance, to fill in missing metadata. So suppose that you have these labels on nodes, where you live, what moves you like, your politics, your gender, your age, and so on. And maybe some of these labels are missing or some of them are wrong. And maybe your goal of finding communities is to somehow fill in the missing ones. Well, if that is your goal, then that's going to give you one notion of accuracy. But here's another goal, which is predicting missing links. So a lot of networks, our data sets are incomplete. My favorite example is the food webs. So, I think that because of the interest from computer science and because of the popularity of online social networks, we like to imagine that we know the graph, or that Facebook or someone knows the graph. Well, for things like food webs, to get that Antarctic data set, someone had to sit in a boat and be really cold for a long time and open up the stomachs of things and look through binoculars and see who's eating whom. So for a lot of networks, it takes real work in the laboratory or in the field to find nodes and links. And so there'll be links that we don't know about and nodes that we don't know about. Okay, so another way to measure the accuracy of an algorithm, like the block model, is take the links you know about, use that to fit the block model. Now the block model assigns every pair of vertices a probability of being connected. Use that ranking to try to reconstruct or predict the links you don't know. Okay? So this is a completely different notion of accuracy, and now this notion of accuracy might disagree with the fill-in missing metadata notion. So all I'm saying is, once you get away from the math problems and out into the real world with the science problems, then I don't think that there is a single best algorithm or a single best model or a single most accurate community structure. I think it depends on your application. That's all I want to say. Okay. How long did that take to say? All right. Good. So we can argue more about this or talk more about this. But now let's do some math. So just to remind you the notation, so Ti is the type of node I, and it belongs to this set 1 through k if I have k different types of nodes. And the probability that there is a link, an edge between I and j is p sub the type of I comma the type of j. And I'm interested in the sparse case, so this will be 1 over n times another matrix, which I guess we could, again, say the same thing. And we're also going to focus on this popular special case where C sub, if R and S are 2 of these k groups, where this is C in if R equals S, and C out if R is not equal to S. So we have C in on the diagonal and C out off the diagonal. And yesterday I defined this quantity lambda in the following way. So if we take this matrix, it's handy to normalize it by the sum of its columns. And what are the sum of the columns? Well, let me remind you that the total average degree, the total number of neighbors you have on average, is this. Okay, because, for instance, you have n over k vertices in your group, and you connect to each one with probability Cn over n. So you get Cn over k on average neighbors in your group, and C out over k in each of the other groups. So the total number of neighbors on average is this. So the sum of a column here is then just the numerator, C in plus k minus 1 times C out. And so if I divide by this, Then I get a stochastic matrix. By the way, we're all friends here, so I would be grateful if I use some piece of jargon that you don't know, just stop me and say, what's that? Okay? Because this is supposed to be a broad audience, so I don't want anyone to feel embarrassed, if I'm more than happy to explain a technical term. So just be, it's very rude not to stop me and ask me if I say something you don't understand. Okay? All right. Good. So I can write this in the following way. It's lambda times the identity matrix plus 1 minus lambda times this matrix where all the entries are 1 over k, where lambda is just C in minus C out over KC. So I mean, if you stare at this for a moment, it will become clear. I mean, the off-diagonal terms are all here, the on-diagonal terms are here, and lambda is just the difference between the on-diagonal ones and the off-diagonal ones. But lambda is also the second eigenvalue of this stochastic matrix. So a stochastic matrix is, because its columns sum to 1, if you have a column vector over here, which is the probability distribution of the type of 1 node. So for instance, I could have the probability distribution of node I, and then if I know that there's a link between that and J, the probability distribution here will be this matrix times that k-dimensional vector. It will give us a new k-dimensional vector. And stochastic matrices, their leading eigenvector is always 1, because there's always some probability distribution which is stable, fixed under the matrix. And in this case, that's just the uniform distribution. If I take this and multiply it by 1 over k, 1 over k, 1 over k, I'll get that same vector back. Okay? And that's saying that if this is equally likely to be in any group, so is this one. So this is the second eigenvector, eigenvalue of this matrix. And what I said yesterday is we can interpret it in the following way. Lambda is the probability that the link simply copies what group I belongs to and makes sure that that node J belongs to the same group. And with the rest of the probability, 1 minus lambda, we randomize J's group as if the link were not there at all. Okay, so that's the notation I'm going to use. And when I drew this graph, new color. So once we have this notation, then it's kind of handy, rather than using C in and C out as our parameters, it's kind of handy instead to use lambda and C as our parameters. So lambda is the strength of the community structure, the probability that groups get copied across edges, and C is the overall density of the network. And if we hold lambda constant and increase C, then we expect the problem to get easier. And so I had this graph yesterday where here is the accuracy that we can achieve, and I claimed that we had a curve kind of like this. So the first thing I want to do this afternoon is explain why this particular threshold, why we would get something happening when C times lambda squared equals 1. That when C times lambda squared is bigger than 1 over here, you can start to make progress. Yes? Exactly. A particular node I and a particular node J. For each such pair of nodes, the probability that there's a link between them is given by P. P is a K by K matrix. So you look up the type of I and the type of J, and that tells you. Well, they can be any real constant, actually, because the p's have to be between 0 and 1, but we're looking at this sparse case where the p's are order 1 over n. So, it could be that Cn is 20 and C out is 3 or something like that. Okay. All right. Good. So, one way to explain what's going on here is a lovely problem which is quite classic called reconstruction on trees. And I don't know the full history here, but I believe that this goes back to a kind of question in genetics and phylogeny. So let me explain the idea. Let's suppose that there are black rabbits and white rabbits. I mention rabbits because, as you know, they reproduce asexually. So here at the root of a tree, there is a rabbit which is one of these two colors. And then at each step, it has a certain number of children, which on average is C. Okay? So in particular, it would be Poisson distributed with mean C, but actually, don't even worry about that for the moment. Say it has C children on average. Now, when it has children with probability, let's say lambda, for each child independently with probability lambda, it's the same color as its parent. And with probability 1 minus lambda, the genetic information is lost and the child has a random color, which might be the same as the parent, with probability 1/2, but also might not. Okay? So whenever lambda is bigger than 0, the total probability is the same as its parent is bigger than 1/2. If lambda were 0, it would be 1/2, 1/2. Okay, good. So now, the rabbits continue to propagate, and T time steps later, I already used T, let's say L generations later, there is, as you know, a very large population of rabbits. Some of them are black, some of them are white. Now, I'll be generous and I'll actually show you the entire family tree. Okay, so you know the structure of the tree. So now you see these rabbits, and I hide from you all of the colors of the rabbits before in the tree. So you're only allowed to look at the colors of these rabbits, and the question is, how well can you guess the color of the ancestor? And the claim is that there is a phase transition above which you can guess the color of the ancestor better than chance, in the sense that you'll get it right with probability bounded above 1/2. But that below this transition, the probability of getting the ancestor right will tend exponentially to 1/2 as L increases. Okay, so you should think of L being large. Good, so it's a nice sort of information theory inference problem. And I am not going to prove to you that this is the threshold, but I will wave my hands and try to justify this. Okay. So here's the idea. If I have C children, and then each of them have C children, then, on average, we have C squared, and down to C to the L. And each one of them has a path through the tree. And now each step in this path, with probability lambda, the information gets transmitted, and with probability 1 minus lambda, it's as if it's cut. Okay? Good. So, well, the probability that the information gets all the way through is lambda to the L. Okay, that on every step it gets through. And so the average number of descendants for which the path went all the way through is c to the L times lambda to the L. Okay? So it's clear that if c were less than 1 over lambda, then probably no information would have gotten through. But it's not enough for just a few paths to get through. So let me wait. Here's the hand-waving part, all right? Let's ignore the fact that a lot of pairs of rabbits here are siblings or cousins or second cousins. Let's pretend that they're independent. Well, because most pairs of them are not closely related. Blah, 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 hand-waving, all right? Well, in that case, it's not enough for just a few paths to get through. We need enough of these paths to get through to overwhelm the noise that you would see here anyway. So in other words, out of this many, we would typically see an imbalance of square root. We would typically see about square root of c to the L more black rabbits than white rabbits if they were all independent coin flips. So the number of rabbits that are really related, that are guaranteed to be the same color as the ancestor needs to be significantly bigger than that. And now we take the Lth root and divide by square root c, and we get square root c times lambda needs to be bigger than 1, which is the same as saying that c needs to be bigger than 1 over lambda squared. Okay? Any questions about this? Yes? It's the standard deviation of the binomial. Again, forget this. It doesn't really, I mean, all that matters for this is that the average number of children is c, and that the distribution isn't too crazy. I mean, I want the typical number of descendants at the after L generations to be c to the L with some concentration. This square root is that if you have c to the L rabbits and each one is just a coin flip, right? So the point is that every time the information doesn't get through an edge, everything below there is random. Okay? Now they are correlated with each other, but I want you to ignore that. Okay? So the point is that if I flipped c to the L coins, then I would expect roughly square root of c to the L more black ones or more white ones. So in order to get a clear signal that the ancestor was black, I need the number of rabbits that are guaranteed to be black because the information got through to be significantly larger than that noise. Okay? So, yes? Oh yes, C should definitely be greater than 1. Yeah, otherwise it dies out with probability 1. All right, so this has been made rigorous, but I think this is still a pretty good intuition about why this is the right threshold. And so there's a paper by Janssen and Mossel where they define a clever kind of definition of how, a clever information theoretic way to make this argument rigorous. So now what's the analogy here? So imagine that I'm trying to figure out, let's say that I have just 2 groups, as in black and white rabbits, and I'm trying to figure out the type of this node. So it has neighbors, which are like its children. It has next nearest neighbors, which are like its grandchildren, and so on. And we go out some radius L. And one thing which is important about this model is that in the sparse case, short loops are very rare. So if you're familiar with the Erdős-Rényi random graph model, for instance, in the sparse case, again, you'll have, in the entire world, you'll have typically some constant number of triangles, some constant number of loops of length 4, and so on. But if you look at almost all vertices, then their neighborhoods out to any constant radius are trees. Okay? At which point, if you study real networks, you should say, well, this model's completely insane then. Every real network has tons of short loops. Yes, I know. So we'll talk about that more in a moment. But the fact that this model is locally tree-like almost everywhere makes a lot of things easier to analyze. Okay, so the intuition here is that even if I magically told you the true labels of all of the nodes at the edge of this graph, then trying to propagate that information backwards or inwards to the central vertex, to the ancestor, becomes impossible if C is below this threshold. Okay? And this argument was made rigorous by Massel, Niemann, and Sly after my friends and I conjectured it in the physics literature. So now, but there's a hitch. The algorithm that I described here, I guess I didn't say this clearly before, but let me say it clearly now. The algorithm is simply take the majority color of all of the descendants. Okay? That's what I was trying to say before. And in order for there to be a strong majority, that's why you need the number the same as the ancestor to overwhelm this noise. But it's not clear that's the best algorithm, right? I mean, certainly in this setting, you know the graph. So let's imagine, it's true, you don't know the colors of all the ancestor rabbits, but suppose you know the shape of the tree. Well, then you might be able to do something better than taking all of the rabbits, shaking them up in a big bag, and just counting how many are black and how many are white. It is an interesting and non-trivial fact that for two groups, the optimal algorithm is simply taking the majority. But for a larger number of groups, you can do better, information theoretically. So for a larger number of groups, it is not the case that when C is below this threshold, there's nothing you can do. And that's also why it seems that for by the way, k greater than or equal to 4, there is still this threshold above which we know you can make progress, but we also know now that you can do better below there. But we don't have an efficient algorithm. Okay. So the exact threshold here is not known, but it's bigger than 1 over lambda. So 1 over lambda is not enough. You need more than that. Okay, all right. So let's see, I'm going a little slower than I expected, but let me now describe an algorithm called belief propagation. All right. Any questions about this before I proceed? So 1 over lambda here would be somewhere below there. So I think that 1 over lambda would not be enough. The threshold, which I'll sketch a proof of tomorrow, is that the information threshold is roughly this. So it scales as log k over k times this threshold, but it still scales as 1 over lambda squared, which remember is bigger than 1 over lambda because lambda is between 0 and 1. So 1 over lambda is somewhere farther down. All right, good. So let's see how much farther we can get today. So let me erase this. So now I'm going to describe this algorithm called belief. Is this bright enough to read? Blue? You read the blue? Not so much? So belief propagation. And belief propagation, I think it goes back to Judea-Pearl and to this whole field called graphical models. But it is also equivalent to something that was rediscovered in the spin glass community in physics called the cavity method. So I think today I'll be able to explain the idea, and that will have to do. So the idea of belief propagation is that each node in your network is going to send each of its neighbors an estimate, which I will call mu I to j sub r. Please forgive the superscripts and subscripts. This is i's estimate that it sends to j of the probability that I belongs to group R. Okay? So everybody sends each of their neighbors a little k-dimensional vector saying to that neighbor your current estimate of the probability that you belong to each of the k groups. But the interesting twist is that you don't have to give the same estimate to all of your neighbors. And specifically, when you talk to a neighbor j, you base your estimate on what you're receiving from all of your other neighbors. Whereas when you talk to each of them, you would include j in that estimate. All right? Why should we do this? There are a couple answers to this question. There's one in terms of variational methods this corresponds to finding an approximation to the posterior distribution that has a certain form. But let me just tell you the kind of cutesy story. Suppose that you go on a talk show with a fellow scientist friend, and the host asks you, what do you think about climate change? And you say, well, I've heard from some scientists that climate change is a hoax. And then the other scientist, your friend on the show, says, gee, I just heard from a scientist that climate change is a hoax. And then you say, hey, I just heard from another scientist that climate change is a hoax. And you go back and forth like that, uselessly amplifying the information. Of course, this would never actually happen. No talk show host would allow such a silly conversation to occur. But, what we need to do is bring in fresh information into the conversation from other parts of the network. So that's one justification for this. Now, let me write down the actual sort of update equation we would do, because the idea is that these things are being passed all around, and we're going to update them. You typically do this asynchronously. You choose a random vertex and update its messages based on its incoming messages. And we're going to do this until we reach a fixed point. And we hope, first of all, that we do reach a fixed point. The process might not converge. Second of all, we hope that when we reach a fixed point, that these are good estimates of the actual posterior distribution. Okay? So those are hopes. And sometimes those hopes are true. So how do we do the updating? Well, I'm going to write this down, but it's really just Bayes' rule. So at each step, you would update what I says to J about belonging to group R in the following way. You would take the product over all of I's other neighbors, so K also connected to I, but not J. And then each of these neighbors are sending to I an estimate that we need to sum over all possible groups that each of those neighbors could belong to. Here is the probability that they're each telling I that they belong to group S. And then because there is a link between them, we would give this message a weight proportional to the probability that there is a link between them. And given the time available, I don't want to derive this, but it's really just Bayes' rule. Okay? So again, what does Bayes' rule say? It says that the probability of the labeling given the data is proportional to the probability of the data given the labeling, where it's a uniform prior, blah, blah, blah. So here's the probability that there would be an edge there if indeed K were in group S and I were in group R. And then, since we need to normalize, we just divide by some normalization, which is just the sum of this over all R. So we don't even need to worry about that. You could just put proportional to if you wish. But you're saying, Chris, how can you possibly just take a product over the neighborhoods? I mean, really what you need to do is look at the joint probability that our neighbors are various combinations of states. By taking a product, haven't you assumed that the neighbors are independent of each other? Okay? Yes, we have. So this is called conditional independence. And specifically, we've assumed that our neighbors are independent if we condition on our own state, or to put it differently, we've assumed that our neighbors interact only through us. So this is a big assumption, and it is exact only on trees. So if the graph were a tree, this would be okay, because then our neighbors would only interact between us. But of course, on any real network, there's probably some path that connects them. Yes? Well, so for instance, suppose that the neighbors are correlated, that half the time they're both black and half the time they're both white. Averaging over those two possibilities, I would just get a different formula than this one. Well, no, we're talking to J, so I'm sorry. So right now, we're updating our estimate that we give to J, and we're doing that based on all the other neighbors. But what I'm saying is that if the neighbors were correlated, I mean, what this really should be would be the sum over all possible combinations of groups our neighbors could be in of the probability of that joint event times the probability that I is in group R given that event. And by writing this as a product of individual sums, we're assuming that this distribution is a product distribution, that they're independent. Okay, good. So, all right, now for synthetic networks generated by the block model, remember they're locally tree-like. Short loops are rare. And under those circumstances, if we could prove that correlations decay somehow with distance, then it would be true in the limit that our neighbors are independent of each other. But my network has triangles. They're directly connected. Yes, okay, all right. So if you want to try this out on real networks, all I can say is it seems to work pretty well. For real networks that have lots of short loops, we currently have no theoretical guarantees of how badly our estimates will be off because of this assumption. But we've tried it, and it's really fast, and it works pretty well, and it seems to be competitive with everybody else's favorite algorithm. Okay. Good. Yes? Sometimes numerically you want to do that as a trick to aid convergence. So people call that damping. So if you wanted, rather than updating to this, you could update to some weighted average of your previous value in this. But this isn't usually a big issue here. Yes? Well, you run around doing this and you terminate when none of the messages change by more than 10 to the minus 8. So as a numerical procedure, you would have to choose some convergence condition. You can show that on a tree, it actually converges in a finite number of steps. Basically, you sort of go in from the leaves and then back out to them, and then you're done. On a general graph, it'll take a while for things to settle down. All right, good. So, by the way, why do I like belief propagation? Something which I didn't say yesterday is that, right, so I kept saying yesterday, we don't just want the best labeling, the most likely labeling. So what do we want? Well, I claim that what you want is to compute these marginal distributions. So forget who you're talking to. Every node has some true probability that it belongs to each group. And computing these marginals would be nice. It would be nice to know that Rajmohan is in the blue group 99% of the time, and that I'm in the blue group only 60% of the time. So we're both in the blue group, but maybe I'm sort of closer to the edge of the blue group. Maybe my blueness is a little bit wobbly. I'm considering joining the reds or something like that. All right. So you would want to know these probabilities. Moreover, it's a theorem that if your goal is to maximize the number of nodes colored correctly, then the best thing to do is to compute this marginal, which might be hard, but let's suppose you could, and then you would assign each node to its most likely group. And note that assigning each node to its most likely group is different from assigning everybody to the most likely joint labeling. All right, so this, let's see. I'm not sure I want to spend more time on this, but I claim that this is the thing you really want, these marginals. Now, so a lot of you are familiar with Monte Carlo algorithms. So one way to compute these marginals would be to run around doing what people call metropolis or Glauber dynamics, where you choose a random vertex and you consider changing what group it belongs to, and you do that with some probability that depends on, how much more or less likely that would make the graph. And you could do that until you reach equilibrium. The problem is, I would argue that that's actually too slow for our purposes. One reason is that these marginals require you to sample from the equilibrium distribution many times in order to get good estimates. So I like belief propagation because when it works, it deals directly with the marginals. Okay, the marginals are its bread and butter. They are the variables that it's trying to update. All right, good. Now, we've written down the BP update equations, and I said at the end yesterday that a particular thing could go wrong. What could go wrong? Well, what could go wrong is we could fall into a kind of silly fixed point. So if you look at these equations, at least in the case where the groups are of equal size and where the matrix here has this simple form, there is a silly fixed point where if all of these are equal to 1 over k, if everybody is currently estimating that it's equally likely to be in every group, then you'll continue to estimate that. It's a fixed point of these equations. So then an interesting question is this trivial fixed point stable or unstable? Okay. So if it's stable, then maybe we fall into it and then we do no better than random coin flips in our labeling. If it's unstable, then maybe things are good. Maybe if you start with some random perturbation, you move farther and farther away from the trivial fixed point, hopefully toward the truth. Okay? So how do we figure out whether this is stable or unstable? So if you've seen dynamical systems, you know that what you should do is look at the, oh, right, blue wasn't so good. You should look at the matrix of partial derivatives. At this fixed point. So this is a big matrix because the entire dimensionality of the space here, if we have m edges, then in each direction we're sending a k-dimensional vector. So this is a 2 times km dimensional matrix. So that might make you a little nervous, but it's not so bad. So does everybody understand why this is the thing to think about? So what we need to do, right, so in this high dimensional space, here's the trivial fixed point. If I have a little perturbation away from this, as I update, the question is, does that perturbation decay and I fall back toward the fixed point, or does it move out along some eigenvector of this matrix with eigenvalue bigger than 1? All right, so this is a kind of standard thing in the, figuring out using linear analysis whether a fixed point of a dynamical system is stable or unstable. So I know that I'm almost out of time here, but in fact, this matrix has a very nice description. Oh, I shouldn't have erased that. So the first thing to notice is that by definition, the only thing which affects these messages are these messages. So one of the things in here is a matrix I will call B. And what is B? It's a matrix that lives on the edges, and if you don't mind my rearranging this a little bit, it says information gets transferred from this edge to this edge only if this edge connects to that edge, first of all, and we don't immediately turn around and go right back the way we came, because when I don't base what J is telling me, you know what I'm trying to say? When I send my estimate to J, I don't listen to what J was telling me. So one condition is that these things match up, but the other is that they're not simply reverses of each other. So this is called the non-backtracking matrix. B stands for non-backtracking. In the graph theory community, it is sometimes called the Hashimoto matrix. So what it does is it describes walks on the graph where the rule is you can do whatever you want except turn around and go right back the way you came. Hence non-backtracking. So this is part of this matrix. The other part is a little k by k matrix which says how much effect if I perturb this message, making it slightly more likely I'm in group R, how much more likely to first order does that make the probability that this node will tell this one that it's in group S? And that matrix has a very simple form. It is simply lambda times the identity minus this flat matrix. All right, so that's just a bit of algebra, which you can do for yourself if you like. But so what this is saying is that if indeed the information gets transmitted a lot, then as you expect, if the probability that this is in group R goes up, then the probability this is in group R goes up as well. And this is just sort of normalizing things because the total probability coming out of here has to remain equal to 1. So this symbol means tensor product, but don't worry, we're not doing general relativity or something like that. All I mean is that this is a big matrix of zeros and ones. Replace each one in this big matrix with this little matrix. That's all I mean. Okay, good. Now, let me say one thing before I let you go. So, this matrix has information from the model, the block model, including lambda. and information from the structure of the graph. The question is whether this matrix has any eigenvalues bigger than 1. That's when that trivial fixed point is unstable. I'm not going to prove that when it is unstable that it points in the right direction, but indeed that's the case. So I want to, can I have 5 more minutes? But give me a number. 5 minutes, okay. So as many of you know, one popular method of clustering nodes and graphs and clustering lots of other things too are spectral methods. So what's the idea of a spectral method? So let's take the adjacency matrix, which is just 1 if there's a link between two things and 0 if there isn't a link between two things. And suppose you have a graph with 2 communities and relatively few links between them. Then imagine that I applied this matrix to a vector which was positive over here and negative over there. Well, what does this matrix do? If we normalize it, it replaces everybody with the average of its neighbors. But, well, if there really are 2 communities, then most things over here, their neighbors will mostly also be positive. Most things over here, most of their neighbors will be negative. So if I have a vector, an n-dimensional vector, which is positive here and negative here, then it will be roughly an eigenvector of this matrix. Okay? And you can phrase this in a lot of ways. You can also phrase it in terms of random walks. To a physicist, you would say that this is the slowest deviation away from equilibrium the deviation that will take the longest to decay if we were doing diffusion, because it takes a long time for the positives to cross this narrow bottleneck and cancel out the negatives. But there's a problem. If you look at the adjacency matrix, and there was a talk, I'm sorry I forgot your name, somebody talked about the spectrum of random matrices in a talk on Monday. Well, random matrices, including the adjacency matrices of random graphs, have lots and lots of eigenvalues. And if you made a histogram of all these eigenvalues, then asymptotically it forms roughly a semicircle. So then the question is, all right, there's some eigenvalue associated with this, which depends on how well separated the 2 communities are. If that eigenvalue is out here, your spectral algorithm does well, because you ask it for the eigenvector associated with the biggest eigenvalue, it finds this one, and then you look at that eigenvector, and lo and behold, it's mostly positive here and mostly negative there, so if you label the points according to whether they're positive or negative, you do well. But if that eigenvalue falls inside here, inside this bulk, what's going on is that there are lots and lots of other eigenvectors inside here with these eigenvalues, and these eigenvectors look essentially random. So your community information gets lost in this bulk, and your algorithm just fails miserably. It returns a classification which is uncorrelated with the community structure. Now, there's a nice paper by Nadekuditi and Newman showing that if you do the calculations using this random matrix theory and you ask when this community eigenvalue crosses this bulk, you get this same threshold. I think this is nice. This already gives you a hint that this threshold is algorithm independent, that it wasn't, that you get the same thing from multiple different types of algorithms. But there's a problem. There's a fly in the ointment, which is that this semicircle law only holds when the graph is fairly dense, when the average degree is log n or so. When the graph is quite sparse, several things go wrong. One is that you actually get noticeable deviations from this shape, but in particular, you get rather large eigenvalues from the following mechanism. And I'm almost done here. Somewhere by chance in this model, there is a high degree vertex. Okay? That high degree vertex, let's say it has degree D max. The adjacency matrix keeps track of all the ways to move to your neighbors. And so the matrix square of the adjacency matrix counts the number of paths of length 2. But there are D max paths of length 2 that go out from this matrix and back to it. So that means if I had a vector which was 1 here and 0 everywhere else, and I applied this matrix twice to that vector, and then took the inner product, the dot product with what I have left, I would get D max. And that means that A has some eigenvalues which are at least square root D max, at least in absolute value. What's going on is that if you ask your spectral algorithm, show me the eigenvector associated with the biggest eigenvalue, what it shows you is an eigenvector concentrated on one of these high degree hubs. Those are the eigenvectors that dominate, and you don't get to see the global community structure. Okay, so these high degree hubs will screw up the algorithm. By the way, for some people, these are features rather than bugs, because some people want to use spectral algorithms to find the hubs instead of find the communities. Anyway, but for us, they're bugs. Good. Well, but the solution is right there on the board. The non-backtracking walk prevents you from doing this. And as a result, it cleans up these localized eigenvectors, and what it leaves you with is a very nice separation between the community eigenvector that you care about and, well, it's not a symmetric matrix anymore, so its eigenvalues live in the complex plane, but you get this very nice disk here whose radius is square root the average degree. And even in the sparse case, this disk, its boundary stays very nice and well defined, and the community eigenvalue that matters doesn't cross here until this threshold. Okay. So the lesson here is that looking at the linear stability of belief propagation in the vicinity of the trivial fixed point gave us a linear operator, the non-backtracking operator, which does a better job for spectral clustering in the sparse case than the adjacency matrix does, or also the graph Laplacian, or the random walk matrix, or the other kind of matrices that people like to use for spectral clustering. Yes? The normalized Laplacian has a different kind of localized eigenvalue, which is that, right, so suppose that let me talk instead about the random walk matrix, which amounts to roughly the same thing. So the other thing that can happen is you have little dangling trees hanging off your graph, and a random walk which enters one of these trees could rattle around inside it for a long time before exiting. Somewhere in the graph there is a worst tree whose size is roughly log n. And that will produce a spectral gap of about 1 over log n. So that's a different sort of localization that you can get. And the non-backtracking matrix fixes this problem too, because it just flies off the end of the tree and dies off one of the leaves. All right, so I may or may not tomorrow do the derivation for you that this spectral thing gives this threshold. But the nice thing is that if you generate these graphs, if you try the standard spectral algorithms, they fail somewhere above the threshold. But if you try spectral clustering with the non-backtracking matrix, it goes all the way down to the threshold. And indeed, it's almost as good as belief propagation. And I think this is cool because it's saying that here's the trivial fixed point. Belief propagation as it updates would go, say, here. The spectral algorithm does this linear analysis and it says, oh, well, I'll guess that that's the truth. And the angle here is actually not very big. So the accuracy of the spectral algorithm is almost as good as what you get from the nonlinear process of running belief propagation until it converges. Okay, so I think that's good enough for today. What I want to do tomorrow is this question of, can you tell whether the graph was generated by this model versus a null model, which is just the Erdős-Renyi random graph of the same average degree. So blur out all the structure, keep the average degree the same, have no community structure at all. Can you tell whether that's how I made the graph or whether this is how I made the graph? And there we'll look at things like the likelihood ratio between the two things, and we'll sketch how to prove this bound about when it's information theoretically possible to tell the difference between these two models and to label things better than chance. Great. And we have until 7 for dinner. Lots of time for questions. Yes. So I think when people implement these things, they often choose a random vertex and do exactly what you said. And that's convenient because, well, it's erased now, but we had a product over everybody but I, so numerically it's convenient to compute the product over everybody, and then I divide out your message when I talk to you, I divide out his message when I talk to him. So that saves a little time. I mean, the only danger with asynchronous updating is that often you can get oscillations. And so that's the usual reason why people do asynchronous updating instead. So, yeah, but you can also get rid of oscillations using the damping trick that he asked about. Any other questions? Yes. Oh, yes, you were the one who talked about random matrices.
But there is some concept of like looking at a few large eigenvalues and then somehow doing a brute force search in the span of those eigenvectors.
Yeah.
Do those things help?
I don't know. I've been learning about this, and I know, for instance, this is also a way to speed up semi-definite programming by looking at this span of a few things. So you're restricting to a low-rank subspace. So I know that this is an important idea. I think, though, that once you're below this threshold, I'm skeptical that there's any information at all that you can get out of the eigenvectors of the matrix. Although, well, it's a little confusing because, of course, the eigenvalues and eigenvectors tell you everything. So, but I think that if you look at any finite number of them, my guess is that you can't do anything. But I don't think we have a theorem to that effect yet. I mean, I think we know that the leading eigenvalue is uncorrelated with the communities. I am not sure what we could say. I would have to ask some people who really know about random matrices about, can you show that in some sense jointly the first 10 eigenvalues are still uncorrelated? I'm not sure how to define that. So maybe that nothing in this, maybe you could show that there are no vectors in the entire subspace spanned by the first k eigenvalues that are strongly correlated with the community structure. I don't know how to prove that, but I think that's a good question. So, I mean, if you are a theorist who likes proving theorems, there are a lot of open questions here. I mean, there's been a lot of progress quite recently, but there are still a lot of open questions. Any other questions? All right, great. I will see you tomorrow.